In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 3, Yield Criteria. Part 1. What do we learn in this chapter? We want to answer these questions. What is the yield criteria? What are the conditions for a yield criteria to be valid? How could we know if a material yields? What is the difference between different yield criterions? What is a yield function? How a yield criteria is verified? Yield criteria and plastic deformation. Okay, in this slide we want to know generally what is the criteria for material yielding. As you can see, this is a general function of stress. F sigma ij is equal to 0. So what is that bar on the top of this sigma? That bar on the top of sigma bar ij means that this is a function of a stress. In other words, this is a function in terms of sigma x, y, z, x, y, etc. and also in terms of principal stresses or other stresses or deviatoric stresses, any kind of stress. So this is a very general notation. F sigma bar ij. Sigma bar also means that effective stress or average stress as well. Okay, so F sigma bar ij equal to 0, we say is a function that indicates, if it is equal to 0, it indicates that the material has yields. What are the conditions for yield criteria for material yielding? Okay, we want to derive this function because this is general notation. We want to derive a specific function for yielding, for material yielding. So we have to know that what are the conditions. For instance, we could say that in tensile stress, if we increase the load in the axial direction, we will reach a point when the material yields. And we will say that as soon as the stress in the material reaches the strength of the material, the yield strength of the material yields. And we have already explained that what happens is that as the stress is increased, the component of stress on different slip planes will increase as well. So we have a slip planes and a slip directions, which we call it a slip system. So one of these slip systems reaches a critical value. I mean, the shear stress on it reaches a critical value, and then yields, material yields. So that's the condition for tensile stress. But what is the condition for a general state of stress? If we have a body under the influence of many stresses in different directions with different magnitudes, what do we do? Now here are the conditions. The hydrostatic pressure has no effect on yielding. We mean here by hydrostatic, we mean the hydrostatic component of stress. Okay, hydrostatic component of stress has no effect on yielding. What else? The material is isotropic. Okay, our material is isotropic. Now I will show you why this is true. Why, you may ask why we assume such an assumption, or the material is isotropic. Of course, this assumption is not true for all materials, but because we want to derive a simple relationship, we use this assumption. Usually, what we do when we want to model a phenomena, or perhaps we want to develop a formula for a phenomena, then we assume a simple model. okay, and derive the formulation, and then after we drove the formulation and we proved that it is correct and we verified it by experimental data, then we will add something to it, okay, to that formula that we have obtained. We will add something to it, and we would say that it will include or consider the effects that originally we have omitted, like the isotropy. So we derive a relationship for the yield stress or yield function, and then for isotropic material, assuming that it's isotropic, and then afterwards we will add some parameters to it to include an isotropy. Okay, so that's how we go about doing things in modeling materials and also in general. The reason is that we want to start simple as possible, and then add the complexity to it later. The third assumption is the Bochinger effect is omitted. Bochinger effect, if you remember, was the effect that in loading and unloading the yield strength was not equal. When you applied a load and you increased it in the uniaxial direction to reach the yield point and pass the yield point, then you unload the specimen and load it in the opposite direction. Okay, opposite direction, compression, in the compression direction. So you compress it after the tensile, after pulling it. So when you compress it and go to the yield point, you will realize that that yield point, the magnitude is not equal to the tensile yield point. And the reason was that the crystals, the orientation of crystals were such that some of the residual stresses which remained in the crystal after loading in the uniaxial direction and unloading, they were tensile stresses, tensile residual stress. And when you apply the load in the compressive direction after unloading, then these crystals with residual tensile stresses were under compressive stresses, so these compressive stresses cancel out those residual tensile stresses, and that's why the yield strength comes down a bit. Okay, so we also omit this effect. Okay, you may say why we do it. As I said, because we want to start as simple as possible, and then later on we can also take this into account by some other means. Right. So now let us see. We set three conditions for our yield criteria. Materials properties should be constant in all directions. Okay, this means the material is isotropic. So isotropy means this: properties constant in all directions. So if it is so, hence the yield function should be invariant to coordinate axis, because directions are to do with the coordinate axis. So if we use this I1, I2, I3 for our yield function, then this assumption will be satisfied, because I1, I2, I3 are indifferent, invariant to directions. To coordinate axis means directions, in any direction. If we go into any directions, the properties will not differ, because I1, I2, I3 are the same. If we define this yield function in terms of I1, I2, I3. Therefore, we say that this F should be a function of these three invariants. Okay, so you now see why we develop this invariance, and obviously these invariants are I1, I2 and I3, okay, in tensor notation, and also in summation of these sigma 1, sigma 2 and sigma 3. Now, we say that the hydrostatic component of stress has no effect on the yield criteria also. So, hydrostatic component of stress. If you remember, we had this deviatoric stresses developed. Sigma prime cube J2 sigma prime and minus J3 and J1 was 0. So if we put the function a function of J2 and J3, then this assumption also is satisfied, and the previous assumption is also satisfied because these deviatoric stresses are also invariant as well, okay, because they are in terms of, we can write them down in terms of I1, I2, I3, so it means that these are also invariants. So the two assumptions so far are satisfied if we put F in terms of J2 and J3. I just went back to chapter 2 to show this deviatoric stress to visualize what we mean. You see, this is the state of stress, that's point P, sigma 1, sigma 2, sigma 3. Now ON is the hydrostatic pressure or hydrostatic component of the stress. Okay, that is zeta here. Zeta is ON and shows the component of hydrostatic pressure because this is perpendicular to OZ. R is perpendicular to OZ. And therefore, if we subtract this component zeta from sigma, we get only R, which is the deviatoric stress. And therefore, as you can see, we said that the hydrostatic component of pressure doesn't have any effect on the stress, so we just have to use the deviatoric components. And I will talk about this hydrostatic component and this assumption that we are saying that it has no effect on the yield surface or yield function. Okay, we say that this zeta has no effect in the yielding of the material. Why it doesn't have it, we'll talk about it later. And the last part says that we assume that there is no Bashinger effect, or Bashinger effect is omitted. Okay, it means that the loading and unloading makes no difference to the yield function. So if we load it in tension and then unload it and then load it again in compression, it shouldn't make any difference. Okay, so how do we incorporate this into the yield function? That's how we do it. We say that the sign of the stresses should make no difference in the yielding. If the sign should make no difference in yielding, then if we make the yield function only a function of J2, here you can see that J2 is equal to that. So if sigma 1, sigma 2, sigma x6, sigma yy, etc. have negative signs, that means applying tension in negative direction, in compressive direction, or positive sign in the tensile direction. It doesn't make any difference because they are to the power of 2. So the result of this expression is always positive, no matter if sigma 1, sigma 2, or sigma 3 are positive or negative, because they are to the power of 2 squared. So if we take this f function of J2, the yield function, then we will have no problem, because we have taken into account all three assumptions by this.